For this, we are using amorphous colloidal glass, and using holographic optical tweezer, we are sharing the system and understanding how the defect will move in the system. So this is my first project. It was done under collaboration of Ratimanisi Sahu and Pawan Kumar. And the second project is on Conan mode in thin crystal. I have only done the instrumentation for this project, and due to fire incident, I am not able to conduct the complete experiment. So this is a colloidal crystal. Here you can see like there is defects by structurally only. We try to understand like what will happen in case of amorphous solid, the same going under the shell. So thereby we can able to identify analogous of these defects in amorphous case. So in 2018, like Oxford Colloidal Group, Dulens Group, they have performed this experiment using holographic optical tweezer for the colloidal crystals, and in their system they use Lager beam and created the share and created these defects, grain boundary defects. So, and these are the defects which were found. And most of the defects are because the share, like they try to orient in certain direction along the direction of the share.
So I just a curiosity question. So what is the defect in a fully disordered material?
That you will define like what is analogous to the defect.
So you will still come to that.
Yeah.
Okay.
In the analysis part. So like here the 75 defects are found. And they are always like oriented in direction of the shear. So we see like such thing will happen in crystal in amorphous solid also, that we are looking like what will happen in case of amorphous solid. So for that I will tell like very fast like what is the principle of optical tweezer. Like if a photon comes from here and goes, and due to conservation of momentum, like this particle will get a kick in this direction, and if a particle from here can go like this, and particle will get kicked in this direction. Since our intensity is not uniform, like there is a Gaussian intensity profile, so there is a net resultant force acting like in this direction. So like particle will get confined in the xy direction, and it will also scatter due to the radiation pressure. So to confine both x and y is already confined, but to confine in z direction also, we using high NA lines, we tightly focus it. So they will create a gradient force in z direction also. And after this focus, there is some point where the gradient force will match the scattering force, and this particle will confine in both x, y, and z direction. So this is like a basic principle of optical tweezer. I mean in the classical image, and we know like light can be treated as electromagnetic wave, and in this case like we know like electromagnetic waves has a momentum density, and momentum density of this electromagnetic waves is along the direction of the Poynting vector. So in the plane monochromatic wave, we see Poynting vector is along the z direction. In a homogeneous and isotropic medium, like Poynting vector is perpendicular to the wavefronts. So when it is perpendicular, and in this case like it is along the direction of the z. And we see like in the Gaussian beam also, we can treat it only as a, if it is below relay length, then we can approximate it as a plane wave. So Gaussian beam only have a linear angular momentum. It doesn't have any orbital angular momentum. So if we use Gaussian beam, we can able to only trap. We can't able to give the shear. So instead of using Gaussian beam for trapping, we are using Lager Gaussian beam. In Lager Gaussian beam, this is the intensity profile, and in Gaussian beam, trapping is happening in this center. But in Lager Gaussian beam, the trapping is happening in this where the intensity is the maximum, in this ring. So there is a phase of e power IL phi. This phase will give the spherical helicity for the wavefronts. So this is the Gaussian part, and this will make sure that there is center donate when R goes to 0 and this intensity goes to 0. So this is how the wavefronts of a Lager Gaussian look like, and you see like if you draw perpendicular, the Poynting vector will instead of going along the z direction, it will spiral around the z. So due to this spiral, like it also have angular momentum part. So we use a linear momentum part to trap the particle, and angular momentum to give the shear to the particle. So I will tell like how we create a Lager Gaussian beam from a special light modulator. So this is the specialized modulator. It has liquid crystals. Based on the orientation of this liquid crystal, based on the voltage you given, it will orient in certain direction, and based on the orientation, it will add 0 to 2 pi phase, whatever based on this orientation angle. So, like if it is completely aligned, it will add more phase, like 2 pi phase. If it is aligned like this, then it will like reflected wave will not get phase added. So if we give the whole panel the same voltage, then it's just acting as a mirror. So if we give like 0 to 2 pi phase like this, so some part will get converted into Linear Gaussian beam, and there will be Gaussian beam also overlap with that, like some due to efficiency of the SLM. So extract just the Linear Gaussian beam, we give a linear grating to this voltage in a linear grating. So thereby like we can get the 0th order and 1st order, and if you overlap both, and in the 1st order we get only the Linear Gaussian beam, and 0th order we get the unconverted Gaussian beam, and we block that using special filters. So we create these circular wells to like this pattern from lithography to make a dense colloidal system.
What is the scale there? What is the scale? Size?
This height is 1 micrometer, and
feature size?
this one, like inner well is 300 micrometer.
1 micrometer.
Yeah, and this we create like one more wing. Like this whole is 500. And we put the silicon particle of 2.32 and 3.34 in deionized water. So to avoid the crystallization, we are using two type of colloidals. If you use single type, then it becomes complete crystal.
So this is more like a size disorder.
Yeah, like based on that ratio of the two, it will depend.
So what is the connection between this photography pattern and what you are trying to do with nanometer? They are micrometer particles.
Yeah, if we not do it, then it will be complete dilute. To increase the density, like if you create a well and if particle keeps on come with time, after some time like its density will increase and we can take the reading.
No, here these are the wells made. Is that?
Yeah, these are the wells only.
The lithography part.
Yeah, this is just a wells.
So inside there is a dip.
Yeah, like these are the white part of the like we.
White part is inside.
Yeah.
White part you have etched.
Yeah, we have etched the white part, and like we created well from.
So what is the benefit? I don't still understand.
If this particle will be here, they will keep on go inside the well,
Yes.
and they cannot come outside. So density of this particle will increase.
Okay. So
Like we want to have like otherwise it become behave like a liquid. We have to create amorphous solid like.
so then you are going to test with optical method that well part. A single well, or collectively you
No, it's a single well. Like we created multiple like to have.
Yeah, so when you are testing, it will be in the single well.
Yeah, in a single well only. Like single strong like.
Sure. I understand. Okay.
Like it acts as a amorphous solid now. Like if we have air refraction more.
Go ahead.
Yeah, I understand.
Yeah. So this is a schematic representation of the holographic optical tweezer. So here we are using 1064 laser. Then we are expanding a beam so it will completely fall on the SLM. And we make sure like the polarization of this beam will align along the direction of the liquid crystals of the SLM. And we give this the pattern I shown earlier to the SLM, and we take only the first order, and using special filters we are removing the other orders. And once we get, and we again reduce the size according to this back aperture of the high NA lens, and collimate, and again we send it through high NA lens. And trapping is happening in this sampling frame. And it is a inverted microscope, and we are taking the image through the bright field microscope. So yeah, this is the same setup. Like you can see, like this is the SLM, and this is optical path is going. And here I will show in a dilute system how the trapping will happen.
So this setup is in Pawan's lab.
No. Yeah, our lab.
Which is?
Yeah.
Which is?
Like you can see, like trapping is happened. And like the particle is also rotated.
So this center I see some circle moving here.
Yeah, like that is where the tracking is happening. And shear like it is not just trapping, it is rotating around circle also. I mean this is only to confirm like we are trapping and able to rotate. And this is our real data, like we increase the density and we take in this like dense system. In this case like we are sharing for this amount of time, around 500 seconds, and then we are seeing like how it evolves after like switching of the laser. You can see the rotation happening inside, and this is the trajectory of the particles. Like during the shear, like this is how it looks, and when shear is not there, like it's doing common motion. See, like even though we are applying only intensity in this way, like inner particle also start rotating due to particle interaction. Like to see this what exactly happening, we plotted this angular velocity with time. Like in the beginning, only particle in the trap they got the angular momentum, but after some time, like due to particle some interaction, like even inner particle get started to rotate. Like the peak increases and it will saturate. Like after some time it will saturate and the whole body acts as a rigid body. And in this region, like shear band is happening. Like we have like different omega for different R.
So is there a medium in which you are doing this experiment, or is
DA
there
button.
Huh?
DA button.
DA water?
Yeah, collides in a DA button.
So that means the interactions are hydrostatically related also.
No, like it is doing domain motion in.
No, but they are rotating. Like
Yeah.
if something I am trying to drag in the water, there will be a length scale over which everything else will be dragged also.
Yeah.
It is a co-moving kind of an action.
Yeah, like here this is hard square only, so due to this motion, like the next also get moved.
But because there is a water medium, if not, if it was only dry
Then it will not do domain also, like it will get stick to the surface.
surface.
Yeah, like this is slightly above. I mean, this is slightly above this surface. It's not exactly staying on the surface.
So
It's a quasi 2D.
levitating because of the water.
Yeah, due to the density.
Density.
Yeah. And like this whole thing becomes saturated and attack as a rigid body, and this region like defect has come. Like shear bending is happening in this region. Like up to here is the whole thing is rigid body, so there is will be no defect. In this region, like we will see how defining defect now. So there is a dispersion is a metric of plasticity deformation. So in this case, like we know like in crystal, if there is a defect, there will be more rearrangement happening around the defects. So if there is a more rearrangement is happening in amorphous, in those regions we call it as a defects. Like particles are rearranging more in those regions. So to clarify that, like there is a append displacement. If you move some particle, like it will get deformed, and each one of them exactly get deformed equally. That part is append displacement, and deviation from this displacement. So we can call any displacement into some, like we can decompose any displacement into append and non-append displacement.
For example, in a solid you have bond angle disorder and bond length disorder.
In amorphous solid we don't have, like in crystal we have like.
No, but you are all in amorphous solid, total, let's say amorphous silicon, all the bond lengths are not equal, right? Or
Yeah.
even the angles are not equal.
Yeah,
So
they are not equal.
So what is the defect we are talking about?
This is not structural defect. These are like plasticity defects.
Plasticity defects. What do you mean by that?
I mean, in crystal, if there is a defect is present, that defect will carry the plasticity if under the shear.
So for example, in an amorphous solid, if I sit on one atom,
Yeah,
its environment in the first shell next cell,
yeah.
okay, of the atomic distribution is different from different each
Yeah,
atom.
it will be, structure is, I mean, structurally not completely, there is short range order will be there.
Short range order is there,
Yeah.
yes, like even XRD.
I
on
mean,
the
I will
first
show
group.
like in the end, like structural order also like different, for this defect particle will be slightly different during shear and non-shear. Like during the shear, like those structural order will be slightly different compared to the non-shear time.
Okay.
So, I mean, we maximize this append part and find the non-append displacement. So, wherever the more non-append displacement is happening, that is the region where we call it as the analogous of the defects. So, this is the displacement plot, and this is the neighbor loss, like how many neighbor it has lost during time. So, you can see like it will exactly overlap in this region. wherever like this one is more, there is more neighbor is blocking, there is more rearrangement is happening. So we find the local maximum for this, like local maximum of this dispersion. And if you look the displacement field of an affine part, I mean non-affine part after removing the affine part, you can see that there is a quadrupolar symmetry. This quadrupolar symmetry in the non-affine displacement only happen in around the defect region. It will not happen like if you plot the same displacement field around here, it will not happen. Only in those regions where the defect is present, like more dispersion is happening, you see a like this two incoming and two outgoing displacement field around it. And this is the azimuthal part. In azimuthal part also you can see there is a orientation of this, like two arrows are going and two arrows are coming like this. So this is the identification of like where the defect
So
exactly present.
is that the definition of a defect?
Yeah, like
is a post-factum analysis of
Yeah,
what
yeah.
happens under plastic deformation.
Hmm.
So it is not that you can, suppose I look at a solid,
Yeah.
okay, I cannot say where is the defect. But now when I go
Yeah,
to a
when share
plastic
is applied.
deformation, wherever something different is happening, that is where
Yeah,
the defect
where-
was or
yeah.
defect is formed.
Yeah, there defect should have present in that region.
Ah,
Because
that's why
like
that
there is,
happens.
yeah, because more rearrangement is happening there. Like in crystal, wherever
So
defect
that
is
is
there,
a post-factum.
yeah, like it is like reverse analogy. Like in crystal, wherever defect is there, we see a rearrangement happening more. But in amorphous, like where rearrangement is happening more, we call it as a defect. So in their case, crystal case, we see like there is all the defects have oriented along the direction of the shape. So we want to see like if we consider only the outgoing vectors and plot their what is the orientation of these vectors, like you can see like there is orientated in this fashion along the direction of the shape. We see like there is during a shape around 45 degree we get a peak, and when the shade is not applying there is no such peaks. So you can think like when plane shade is applied, this expanding component will make around 45 degree with the direction of the shape. In this same like in circular thing also it is almost like it will create 45 degree along the direction of the shear direction, similar to the what they have seen in the crystal. So this is the pair correlation function or radial distribution function. So it will tell like what is the structure of the system. So for it, like what is the probability of finding a particle at a distance r from the center particle. So if it's a complete pure crystal, you will see sharp peak at regular intervals.
5 minutes. No, I gave you 5 extra because we have been asking. Although your 20 minutes are up, but
Yeah. So if there is some peak like this for a complete crystal, for almost ideal gas, you see it will go to 1. But in case of amorphous solid, there will be short range order, and it will go to 1 after some distance. So in our case, during the share, like we share up to 500 thing. So you see like the very high peak in the first, and it will go to 1 around like 3. But when the shade is stopped, the structure has become slightly different. Like you see the peak in the first has decreased, and the higher peaks has developed. Like there is a different in the structure around the defect when you are sharing and when you are not sharing.
So another interesting question is that suppose you do the sharing and you locate defect positions.
Yeah.
Okay, and you say, okay, here where the defects, that's why they move differently.
Yeah.
I remove the share.
Yeah, I mean you are removing the affine part. Yeah.
Yeah. And then again I do. Do I find the defects at the same, there is a memory?
I mean we have taken some oscillatory data. We not did any analysis.
Not oscillatory in a sense that
I mean you rotate it after some
frequency.
time again rotate and
That is very interesting, right? Because plastic deformations,
Yeah.
when they go beyond the reversible limit, then they cannot be brought back.
Yeah.
But if you do below the reversible
these are
limit,
all plastic deformation only.
exactly. So now the question is, if you apply plastic deformation and you locate, let's say 7 defect sites.
Yes.
Okay, now I remove the stress.
Yeah.
And again do the same same shear.
Yeah.
Okay. Are there
Same point.
defect happening at the same point or somewhere else? This was my question.
We not did any analysis.
Okay. But isn't it an interesting question to ask? If there is a memory in the
Yeah.
system?
No, like fidelity.
Yeah.
Till now we only did this much analysis.
Yeah, that's fine. Don't be guilty about it. It's just an interesting question. But what do you feel based on your experience? Will it appear at the same point?
Yeah, we even see like it will take, I mean, the system will deform less time.
Deform?
Less amount of time. Like if it rotated very much in the beginning, like if you do it second time, it will be slightly less compared to the first one.
So you think that the defects which were present, the plastic deformation will annihilate some of them out so that they may slowly, suppose I do 3-4 times,
Yeah.
finally I may realize that there are no defects now.
Yeah.
It's
I mean,
possible.
it get more and more to the,
You can call it mechanical annealing.
yeah,
This is thermal annealing.
like it will go to the minimum more and more.
Yes.
So in conclusion, like what we have done, like we built a holographic optical tweezer and we created share using optical vertex tweezer, and we identify analogous of this defect in using this mean. This mean is a very good parameter in identifying these defects, and we find out like around 45 degrees there is a peak forming along the direction of the shear. Like it is almost similar to what they have, like in 2018 they have observed in Duran group. And in the future work, like we are thinking of doing like oscillatory shear and see like by changing the topological charge of the Laker Gaussian beam. So this is the first project. In the second project, very fast, 2 minutes. It's only instrumentation, so there is no result.
Yeah, go ahead.
So the aim of this like to study phonon mode in crystal
First
using.
was only result for instruments.
We did instrumentation.
Also.
Yeah.
Okay.
Okay, good.
But we also did some analysis. For the second, due to the fire, we not did that.
Oh,
We not able to do any lithography.
yeah.
So phonon modes in crystals under fire. That would have been a title.
Fire trap.
I mean, this is the main goal of this project, like to study phonon modes in crystals using like optical traps using a body. So
What is AOD?
it's a cost optical deflector, and like this is the we can think complete crystal is a spring and ball model. So spring and ball model, like each of same M and K, there is a discrete translation symmetry in a complete crystal. So we want to like look like if we increase some of this stiffness and see what happens. So we know like optical tweezer is a harmonic trap. So if we trap some of them, like randomly pin some of the particles, and it is like introducing defect to the system. Like these particles will be different from the surrounding. Even though structurally they are crystal, but in terms of phonon modes, like it is not similar to the surrounding system. So we will increase the pinning, like concentration of this pinning, and see around which transition like it will go from crystal to amorphous stage. Around what percentage of the pinning it will go to amorphous stage. Okay. To achieve this, we are using optical tweezer, time shared optical tweezer. So the main aim is to like we completely trap only single particle at a time. If we trap this, we shouldn't disturb the surrounding medium. That is the aim, and we are able to trap this large field of view also. That is the aim. So we are using tellurium oxide crystal, and it is attached to the piezo. So once a RF signal comes, then this piezo will oscillate, and there will be sound wave created, and due to compression and reflection, it will act as a grating crystal. So based on the frequency of this RF, you are able to change the direction of this first order. So this is in one direction, and then you use ion lens and just do the same trick what we have done for the previous thing. And this is for single direction. If you create a two-dimensional, like perpendicular these two, you can able to create a pattern like this, and able to trap in each of the wells. So here is set up like see, you can see like there are two perpendicular axes, two perpendicular crystals are there, and based on the function given in the arbiter function generator, like you can able to create any pattern you want. Like any 2D pattern you can able to create and trap in that fashion. So then we using combination of lens to make sure like the trapping plane and trapping plane is matching with the focus of the beam. Using these lenses we are making sure like big field of view and strong enough trapping. And the power here using is around like 2 watt we are using in the beginning, and like after some maybe around 1.5 it is going. After like I mean, there will be first 0th order we are blocking. In first order is around 1.5 watt. Yeah. Because like potential will be divided into each, so we have to like help over to like if you create one more trap, the potential will be divided by each time you increase the number of traps. So this setup, like here we are making it from elliptical to the circular thing. Then this is the AOD. So in this AOD, like using this RF and function generator, we are creating a pattern and sending it through the upright microscope. So in this microscope, we are using like 0.85 NA lens objective, and the rest is like similar. Like white field is happening from here, and this is like the laser path. And by giving the function like this in a function generator, you can able to create like a football court, and you can see like it's around like 100 micrometer field of view, and we are able to create like trapping in such a big field of view, and also like this single particle is getting trapped.
Right.
Like is the function like given like
how do you decide that function? अभी क्रिकेट करना है तो क्या करूँ?
no, like in x, like we keep it x constant, then change the y, so it's here and it will move, then y constant and move the x and it will move like this. And to do this, like you can use sine
So you are
function.
modulating that way.
Yeah, we are modulating the frequency of the RF transmitter by the AFG. Yeah, like you know, we just need to have the location of the points, then we can create any pattern we want. So by using sine and cos, we can create a circle, and by using this some complicated
The
parametric
lower
equation.
one is commensurate with your age.
काम का बता है।
आपका नहीं। क्या
It's a
पता है?
parametric equation given in x and y to create a.
अच्छा एक बार बोलना कि all these experiments this Ganapati, right? Ajay Sood, Ganapati, they do a lot of these experiments with collides and so on. So they basically are trying to see if we can learn about atomic physics, based on large scale systems. That's what I understand from Ajay Sood's lectures and so on. Okay, so here one question about phonons is that in normal solids, because of charges, you have optical and acoustic phonons. But here, you can have only acoustic phonons. That is true,
Yeah.
right? Can you simulate something where we can have two charged spheres?
We can do scattering also, but I don't think we can completely
No, I
take.
mean the two types of spheres
Yeah,
with different charges you cannot mix it.
yeah, we have to make sure like stability of the collide.
That's what
Otherwise, it will
Okay.
coagulate and it will not do domain.
So they will form domains of
Yeah.
two charges and so on.
Mm,
So that will be non-trivial.
I mean, you can see like there is a very big field of trapping and also like single particle trapping is happening. Now we just need to increase the density using lithography and trap few of them. Then the rest analysis will be simpler. Only thing is to create dense. So you can see like this is the final goal, and in this case like we build a time set optical trap, and we build even our own microscope for this thing. And like so that we have more complete freedom of every thing, and we even optimize the whole system to have like large field of trapping and type trapping, around like 200-300 particles are getting. Like in the future work, we are thinking like to integrate completely in the lab to find the position of the particle and send the laser there. Now this whole thing is done using Python.
So why do you need lab?
I mean, it will be slightly faster.
Do you think so? Because you can make Python as much fast as you want depending on what you
Here is
use.
a manual we are doing.
Okay.
Like take the image from LabVIEW and give it to Python, and again.
But take images with something else and integrate with Python. Okay, we can discuss it.
Thanks.
I think we like